Hello friends. Today let's discuss about modular electronics platforms which helps you develop rapid prototyping in industrial electronics, and we also will look at how this modular electronics idea has been implemented in E-LAGOri as a system. I am Dr. Anish Bekel. I have been working on electronics and implementations of systems for last 15 years. I have a PhD from IIT Madras, and uh, I have a working knowledge of being in industries and also in research organizations like ISRO, GE, and Forbes Marshall. Typically, what happens is that as soon as the specifications are handed over to the system designer, he passes it on to an electronics designer and asks them to develop a prototype. Now, once the specification is received, they go on identifying what components are required to create these systems and create a schematic, a PCB, and then get it fabricated. And once it's fabricated, it goes through a process of testing. And when we find that it does not conform to specifications, we go ahead and change it, and this iteration goes on several times, and sometimes, and actually most of the times, you find that the specifications also have evolved, which leads us to build completely different boards, and this ends up taking up more than a year, or in many cases several years, to develop a system, and of course a large amount of money is spent in doing so. If you look at this more analytically, you see that it's about a 53-week process with about 1 week for concept development, about 8.5 weeks for circuit, and then about 4.3 weeks for schematic and layout development. And then you will get into the process of procurement and fabrication. What you will find is that this procurement and fabrication process is quite tricky, because you have to basically get the components and get it assembled, rate the right vendor, and so many other things, which will take more than 13 weeks most of the times. And then you go ahead and bring up the board, and you will find a lot of problems with it, correct it, and sometimes even you have to go back the cycle, and then of course write the software required for the system to work and interface and test. And after all these things, you will most probably find that the board is inadequate, and you will have to repeat this cycle several times to get the board working. What do people do to solve these problems? One is by using eval boards. Every company provides eval boards, but the whole problem with these eval boards is that the eval boards are not at all systematic. In a sense, they have different structures, and they are all made in such a way that they cannot be connected to each other, and we end up putting a lot of wires, and it doesn't work. This forces us to move to the custom design, and you cannot build a system using these eval boards. It is also a problem that we take up constraints of mechanical engineering design too early in the design, because what ends up happening is when it is too early, your concept itself is not proven, and you end up doing a lot of nice looking objects which do not work, right? And then you have high production cost. You also have to deal with EMS vendors who do not really like doing prototype jobs because it takes up too much time for too lesser price. And also you will find that every time a specification changes, you have to redesign the entire system. You also end up with a lot of wastage. I have seen lakhs of rupees being wasted during the prototype development stage, due to the faulty PCBs or faulty designs or whatever is the reason. And also, whenever we have an error, we have to completely remake the board, and a long time is lost in iterations. Now, in order to solve this, several approaches have been tried. I have told you about evaluation boards, and now with the era of DIY electronics, Arduino, Raspberry Pi, and many other such electronic interfaces have created open source resources. But the problem is, again, they are all not they are all not built to the same form, and hence you will end up with a bunch of wires connecting them, and it degrades performance, and also at the right time of a demonstration a wire comes out and you don't know from where it came out, and you end up having problems. Our PCs have always been modular. You could replace RAM boards, you could replace, in some cases, even the processors. You can replace hard disks using a PCI interface by using these kind of slottable hardware, but their functionality is fixed and very, very defined. There is a beautiful system called PC104 which has been used in military and space applications, which are really compact and stackable modular electronics boards, but these are not as famous in the general architecture as it could be, right? Now, in order to create a structure, let's step back and look at how electronics is, right? One of What you see is that there are two kind of systems in electronics in general. One is possibly a digital system, the other being an analog system. Digital systems are mostly bus nature, in a sense that a CPU connects to multiple peripheral devices on a bus and collects data through a bus. It could be a bus which is bidirectional, it could be a single directional, it could be operating multiple of them simultaneously. There could be multiple architectures, but they are always a bus architecture. Whereas in analog systems, most of your systems are running in cascade. In a sense, what happens is, for example, you have a filter, you have an amplifier, you have an analog to digital converter. They always go in cascade. One process performs a function, then it gives it off to the next system performs a function, and then gives it off to the third system. So these are the two distinct things that exist. And now the question basically arose was that, can we create a combination of a system which uses both these methodologies and create a comprehensive architecture which can be used for rapid prototyping? And one of the beautiful forms is a stackable architecture. Now, how do you accomplish this in a stackable architecture? Happens on an E-LAGOri board. So every E-LAGOri board is basically has exactly the same architecture. So it basically has a two column 16 row connectors, which is it has a two column 16 row connectors, and on the left hand side, and a single column 16 row connector on the right hand side. Now the ones on the left hand side are basically used for the control bus. They are called bus section. They are basically control signals and also the power supplies and several communication. I will come to that in the later slide. And on the right hand side, it is purely dedicated for analog transfer of information, and it has a very special structure that I will also explain in a couple of slides. Okay, so every board has these kind of analog sections, one being the pins and then being a socket. Now let's go deeper, and these modules as such are 50 by 50 in size, and in some cases they are slightly bigger, about 65 by 50, but most of our modules are about 50 by 50. Now if you go to the next, let's understand these things a little more deeper. What happens is, if you look at the digital section, there are two columns, and out of the inner column basically contains the entire communication network. So you have everything that corresponds to power supply and communication. It has USB power supply, it has offset voltages, reference voltages, it has 3.3, -5, and it also has I2C, SPI, and some pins for interboard communication, which basically talks between multiple boards and configures things. It also has USB 2.0 capability, and it has a reset button and a ground signal. So all these things are sitting on this, and you don't need to do anything to connect them. Whichever board uses these signals uses those signals. That's it. You don't have anything to deal with it. Now on the left hand side, you see another 16 signals, which are digital signals, which are available for the user to be selected as either clock or maybe chip select for your SPI systems or any other application that might need them. And you can decide which of these pins can enter into the board, or what signals from the board can exit through these pins by using a bunch of jumpers that are shown as yellow jumpers, right here, the golden colored jumpers. Now, how do we short these jumpers is again a topic that I want to discuss, but little later. Now, once you have done that, and even if you look at our specifications also, our data sheet, you will find that this bus section is depicted on the top, and multiple pins of these 16 digital connections are assigned to a same functionality. For example, in one of this motor driver board is assigned to C5, C9 and C13, and you can choose whichever whichever signal you want as those pins. And that helps a lot when multiple boards are stacked on top of each other. Now, if you look at the analog section, it's pretty unique. It has the pins on the bottom and the sockets on the top. Pins are basically considered as input, and sockets are considered as outputs. Now, the pins basically, what do you call, it takes in the input signal, and you can see a bunch of jumpers that are connected to the pins, which decide which signal on the pin should enter into the board. For example, if you short the first jumper, then the signal that is present on the first pin will enter into the board, right? Will enter into the board. Similarly, you have such jumpers on the output section also. Now they basically allow you to decide the output of that board should enter which particular pin. For example, if you short this jumper, then the signal from the output will enter into the first socket. Okay, so this allows for deciding the signal, what signal has to be processed by that particular board, and after processing, that signal should go into which pin. Now, there are cases where we want to basically bypass a certain processing. So for example, certain signal wants to go through a filter, whereas certain signals do not have to go through a filter. So in that situations, what we do is that we also provide a bypass selection on the analog side of things, where you can short this jumper, so the signals from the pin will directly go to the socket from one board to the other, and you can process the signal on the top board. So you have some signal on board 1, you don't want to process that signal on board 2, but rather you want to move it to board 3, then you can short this jumper, then the signal will move from board 1 to board 3. Okay, so this helps us establish parallel connections. Also, it helps us establish to take through multiple signals through the board. Okay, so now how do we short these jumpers? If we had made this entire system using a 2.54 mm jumper pads, then the system would have become very, very big. So in order to remove that problem, what we have done is we have given these jumpers so small that you can use a conductive ink pen to basically write on these jumpers, and within a minute time it will basically cool down and solidify to become a solid connection, which we have tested to be working even after a year, so without any problem. Or at least 3 to 6 months should never be a problem. So by doing this, you can use basically reuse the boards also, because once your once your system is completely built and you want to build a second system, you can always erase it off using a conductive ink pen or by rubbing on it, and you can reuse the same board for any other use, right? So how do you build a system using these E-LAGOri boards? What you do is that you basically draw a block diagram. Once you draw a block diagram, you will most probably find every board of that block diagram, every block of that block diagram as a board in our ecosystem. Okay, so use these pre-made boards and short the jumpers for input, output, bypass, and also digital connection in as per the orientation of the block diagram, as per the signal flow in the block diagram, and then you basically stack these modules on top of each other. Once you stack these modules, your hardware setup is ready. So once your hardware setup is ready, we provide SDKs or libraries for various processors that are available on our ecosystem, free of cost on our GitHub website and on our GitHub. And you can basically download these SDKs and write the program on top of them. Now if you want to modify, it's as simple. By get few more boards and take off the board that is of no use to you. Put up the new boards. Before putting up the new boards, short the jumpers that are required to be shorted as per the new signal flow, and then stack up the modules again in the sequence, write the program again, your modification is ready. So you can optimize on possibly the different kinds of ADCs that are available. You can optimize on various kinds of processes that might be available. You can optimize on various types of amplifiers that are available in our system. You could choose a low noise, you could choose what do you call general purpose amplifiers, you could use zero drift amplifiers. Many of our these modules are available in our ecosystem, and you can use those modules. So various things, it's pretty agnostic to the kind of application that you do. You can do anywhere from a camera, basically using what do you call for the fundus imaging in a medical application, to a strain gauge interface, a spectrometer, or a PLC for industrial control. You can use various of our boards to basically build hundreds of applications that you would want to build, right? And if you want to make it mechanically rugged at the end, we also provide baseboards and top boards that are available, that comes with that comes with threaded studs. You can basically connect a 3 mm screw rod into it and fix it using a nut, and it becomes a very strong rigid system which you can take and use it for testing, or you can take it and take it even for field trials with possibly a reasonable enclosure around it, right? You can contact us at this phone number. You can scan the QR code that is available here, and you can what do you call look at various modules that are available in our ecosystem. And if you